Anin, Bonjour, Sarah Hazel Dijnikos, Nibising Donjaba. Hello and welcome. My name is Sarah Hazel and I'm from Nipissing First Nation. I'm also the project manager for the working group on unmarked graves for the Canadian Archaeological Association. And today I'm going to be talking to you about ground penetrating radar and recommended practices for data collection procedures for locating unmarked graves. Before we get started, I wanted to draw your attention to our online resources, and specifically, we have two comprehensive guides to accompany our video series, and you can visit these at the link provided on the slide. Unmarked graves investigations can bring up distressing content, and it is important to take care of yourself mentally and emotionally while doing this work. Please make sure you have mental health supports in place, or you can call one of the numbers on the slide if you are feeling triggered and you can speak to a health professional. And I'll just leave this up for a moment in case you want to write one of these numbers down. Ground penetrating radar, or GPR, is a form of remote sensing that is commonly used to locate unmarked burials in cemeteries. It works by sending electromagnetic waves from an antenna into the ground at different frequencies. Soil layers and objects below the surface can reflect these waves, returning them to the GPR to be recorded. The time it takes returning waves to reach the GPR allows us to estimate their depth. Different soils and objects will reflect the waves differently back to the antenna, allowing for visualization of the subsurface. This document considers how to collect GPR data when searching for burials and how to interpret potential burials in GPR results. GPR is non-invasive. It does not disturb or damage the subsurface. It is widely used in industrial contexts for the detection of buried pipes, cables, building foundations, and other buried infrastructure. Its use in locating burials is a specialized application that requires a specific method and expertise in identifying grave shaft reflections. When a grave is dug, the soil density and compaction may change, and under good conditions, the GPR signal will reflect differently over the grave shaft. Interpreting these signals as graves takes specialist knowledge and experience, and archaeologists have been working on refining the use of GPR to detect graves for many years. While GPR cannot provide 100% certainty of a burial, graves can be identified with confidence, especially in formal cemeteries given optimal soil conditions. Its application is less well developed in informal or unmarked burials, and certain soils, like clay, can make grave detection challenging. Negative results in GPR do not ensure that no graves are present. It implies further work is needed. It is important to note that under normal working conditions, that GPR does not detect bones or human remains. It only detects changes in soil density and/or compactness suggestive of burial shafts. There are a wide variety of GPR systems available, and it is extremely important to choose one that will provide your investigation with the desired depth of penetration and resolution required to detect graves. One of the most important variables in your GPR survey is the selection of an appropriate antenna frequency. GPR antenna frequencies typically range from 10 MHz to 2600 MHz, and the depth of penetration and the size of the object you can detect will vary depending on the frequency used. Low frequency, for instance between 10 and 100 MHz, antennas can penetrate up to 50 meters, but can only identify large buried objects, whereas high-frequency antennas, 1,000 MHz plus, can detect very small objects, but may be only able to penetrate about 50 centimeters into the ground. There is a trade-off between how deeply you can investigate and the size of the object you want to identify. Most archaeological investigations use frequencies between 250 MHz and 500 MHz, which are ideal for grave detection. You can operate GPR antennas in a variety of ways depending on the environment you are investigating. Four-wheeled systems are the most comfortable and facilitate the mounting of a controller and a GNSS unit. However, they work best on very flat surfaces such as concrete or manicured grass and may not be suitable for rugged, uneven terrain such as a plowed field. Two-wheeled systems are much more suitable for uneven surfaces and are often more efficient at surveying smaller, irregular areas with frequent obstacles, as they can be positioned closer to the obstructions. However, they are more tiring and uncomfortable to operate, particularly over large areas, because the controller and the GNSS unit have to be carried. Three-wheeled carts with large wheels offer a compromise between the two systems. They work better on uneven surfaces than a four-wheeled system and are less tiring to operate because you can mount the controller and the GNSS. Fortunately, the mounting options are interchangeable, so large, relatively even areas can be surveyed with a cart-wheeled system and uneven areas with the two-wheeled types. Before conducting a GPR survey, the area of assessment should be thoroughly investigated and mapped. Landscape features, areas of interest, potential obstacles, and survey grids should be located on the ground and surveyed using unmanned aerial vehicles and/or land-based surveying instruments and incorporated within a spatial data management system like a geographic information system. This will considerably aid subsequent investigations. GPR surveys should begin with an assessment of the geology of the survey area. This is done by collecting a few lines of data in undisturbed regions of the survey area, for instance, that do not have any burials or other disturbances, such as trees, roads, or buildings, to establish what the background radar response looks like when there are no buried objects present. This makes it easier to recognize anomalies or unexpected differences to the background radar response, which might indicate the presence of a buried object. One of the more useful features of GPR survey is that it can estimate the depth of buried objects. In order to do this, it is first necessary to establish how fast the radar wave is able to travel through the ground, which will vary from site to site depending on factors such as soil type and moisture content. While it is sometimes possible to measure this radar velocity directly by calculating the time it takes to travel to and from a buried object whose location and depth is already known, in practice, this is usually not the case. Velocities are usually estimated based on the known average velocities of more common subsurface sediments or through a process known as hyperbola fitting. A hyperbola is a feature observed in GPR results, which looks like an upside-down U and is the radar's response to a small buried object. The shape of the hyperbola will vary depending on how quickly the radar wave is traveling through the ground. Thus, analyzing the shape of the hyperbola helps you determine the velocity of the radar signal. GPR survey is time-consuming. We estimate that a crew of 3 technicians, including a GPR operator and 2 assistants to move the ropes used to guide the GPR, can conduct intensive survey of about 500 to 1,000 meters squared in one day, depending on the conditions. To do GPR survey, it might also be necessary to prepare the area or the site, because GPR units work best when in direct contact with the ground, and this may require the removal of low vegetation and/or mowing long grass. GPR surveys require permissions, access, and the development of agreements on scheduling, deliverables, timelines, training, and if required, budgets. Also, depending on the jurisdiction, permits may be also required. Communities often require certain protocols to be followed, including necessary ceremonies, timeframes, and rules about comportment and behavior when working with ancestors. These all need to be worked out and agreed upon before starting GPR survey. There are 2 basic forms of GPR survey: reconnaissance survey and mapping survey. In both cases, we recommend an antenna frequency between 250 and 500 megahertz. Higher frequencies are sometimes used to investigate a known burial that is very near the surface, for instance within 50 centimeters, but lower frequencies are more useful for locating unmarked graves. Reconnaissance involves roaming systematically over a target area looking for signals in the GPR display. This can be very useful for confirming that probable graves exist within a large area. When a response indicating a target of interest, in this case a possible grave, is identified, the operator scans the area repeatedly to confirm the identification. Potential graves are then flagged and mapped. Ideally, reconnaissance data would be captured as either screen grabs from the display or stored as compilations of lines or traces. Reconnaissance survey is a preliminary step in the GPR survey and should be followed by more detailed investigations. GPR survey data are most useful when collected in grids. These can vary in size, and while experienced operators may survey grids of up to 50 meters squared, they usually measure between 10 and 20 meters square. Grids that are larger than this can take a very long time to survey and can lead to inaccuracies in the position of the GPR. Conversely, numerous, smaller grids are unnecessarily time-consuming to set up and survey. It is likely that you will need multiple grids to entirely cover your study area. It is often helpful to use rectangular survey grids to avoid confusing their orientation during processing, since squares are more difficult to orient because they are equilaterals. Radar scans should be collected every 2 centimeters along data collection lines spaced 25 centimeters apart to provide enough data sampling points to locate burials when using frequencies between 250 and 500 megahertz. Spacing the GPR lines evenly and close together ensures overlap between the lines and coverage of the full area. Burials are most visible in GPR when the survey crosses the grave perpendicular to its length. As the grave orientation cannot be assumed for unmarked burials, the best practice is to collect lines in perpendicular directions, X and Y, across the grid to increase both the signal density and the chances of crossing the short axis of the grave, as demonstrated in the figure here. When working in a cemetery context, where general orientation is known, collecting data only along the axis perpendicular to the grave length may be sufficient. The application of GPR for unmarked graves generally uses unidirectional data collection within grids rather than bidirectional, also known as zigzag. Unidirectional collection is especially important over long distance, for instance more than 5 meters, to reduce distant offset errors from inaccurate odometer calibration and uneven terrain. The grid should be rectangular, laid out using non-metallic tape measures or other survey tools to reduce potential signal interferences. Large metal objects on the surface, such as fences, can create noise in the GPR signal, and care should be taken to minimize interferences. Whenever possible, and especially on sloping terrain, the GPR should be equipped with high precision, real-time kinematic positioning, RTK, GNSS. This allows data to be correctly located on the landscape and corrected for slope, which greatly clarifies reflective patterns. Miigwech, thank you for joining me for this module on GPR data collection procedures. Once again, I'd like to direct you to our online resources, the link which is provided for at the top of this page. Take care.